Hello, so today we're going to talk about antiderivatives and what they are. And we're going to do it from a perspective of a graph and from a table. An antiderivative, you can think of it as being the original function for a derivative. So if f prime of x is 2x, you think an antiderivative is what function would have 2x as its derivative. And one example for my f would be x squared, because the derivative of x squared would be 2x. It's also x squared plus 3, because the derivative of x squared plus 3 would be 2x. So for any one derivative, we're going to learn that there are multiple antiderivatives, and we're going to explore that through graphs and tables today. To do this, we're also going to use the fundamental theorem of calculus. Remember, that says that the integral from a to b of f prime of x dx is the antiderivative, so f of b at b minus f of a, or in other words, the change in f is the integral of the derivative of f. Okay, so here's a graph. This graph is f prime, and again, you have to always pay attention to what graph are they giving me. So here's f prime, and I want an antiderivative. I want a graph of f. And initial conditions are going to be important. So first we're going to draw one when f of 0 is 0. So I'm going to draw this graph over here. I'm going to draw f on the graph on the right. And f of 0 is 0, which means I will start right here. Okay? So if I think about this, what I know is that f of 1 is going to be f of 0 plus how much I change on f from 0 to 1. Otherwise, in other words, the integral from 0 to 1 of f prime of x dx. And so I can go over here and say, well, from 0 to 1, the integral of f prime is this area. And this area is 1 wide and 3 high is 3. So from 0 to 1, I'm going to go up 3 units. 1, 2, 3. So at 1, f of 1 will be 3, right? Because this is 0 plus 3. Right? F of 2, in a similar fashion, is f of 1 plus the integral from 1 to 2 of f prime of x dx. So again, I think from 1 to 2, what's my area under my f graph? That's 3. I'm going up another 3, and I'm going up in a way that I have a constant slope. So my slope is a constant on this part, so I'm going up 3. And similarly, from 2 to 3, I'm going to go up another 3. 1, 2, 3, and I'm sort of running out of space. Now, from 3 to 4, I am still going up, but I am not going up at a constant rate, and in fact, I'm going up more slowly, but I am still going up. I'm going up 1.5. So f of 4, if we think about that, is f of 3 plus the integral from 3 to 4 of f prime. And so f of 3, I was at 3, 6, I was at 9, and I'm going to add 1.5, and I'm going to end up at 10.5 right up here. And if I think about here, I had a constant slope, a slope of 3, and so I was doing this. But now, remember here, f prime is going down, which means f double prime is negative, because f double prime is the derivative, is the slope of f prime. My slope here is negative, and if f double prime is negative, that means my original function is concave down. So as I go from here to there, I am concave down. It's probably not going to bump up like that. It's going to be more, I go from straight to curving. And now what happens from 4 to 5? If I think about 4 or 4 to 4.5, I'm going to start to go down a little bit. Remember, this is negative area, and that's a little bit. So after 4, I'm going to start decreasing a bit. Okay? And again, this whole region right here, f, which this is concave down because f prime is going down. So that's starting off at f of 0 is 0. Now I can get a totally different graph for f built off this same f prime by saying f of 0 is 1. So if I start at 1, now from 0 to 1, I still go up 3, and I still go up 3. Basically everything is is 1 higher than it was before. So my graph looks very similar, but it looks like that. And you can imagine if I said that f of 0 was 5, my graph would be much higher. So my graphs are similar, but they are different from a constant. Okay, let's try another one. So here's our f prime in this case. Sketch a graph of 3 antiderivatives. One with f of 0 is 0, f of 0 is 1, and f of 0 is 2. So let's start with f of 0 is 0. So I'm going to start right here. And again, I have the same idea. All right, so right now we're going to combine a couple different things. We're going to combine how much something changes, but also in what way. So the quantity, but also what's going on. So here's my f prime graph. Right here, from 0 to 1, f prime is negative. So what we know, since that's my slope, we know that f is going down. And f prime is increasing, so f double prime is positive. So we also know that f is concave up. So I'm concave up, but decreasing. And another way you can think of this is from 0 to 1, the integral, this area is -1, right? It's half of the rectangle, too high. So I am going to go down -1, but in a way that's concave up. So from 0 to 1, I go down 1, but in a way that is concave up. Now, from 1 to 2, I go up 1. But again, since f prime is going up, f double prime is positive and f is concave up. So I'm going up 1 and I'm still concave up. Right here, where f prime changes from increasing to decreasing, f double prime changes sign, and f changes concavity. In other words, has an inflection point. So at 2, which is right here, f is going to have an inflection point. Now coming down this way, okay, so f prime is still positive. This is still positive area. F is still increasing, but it is increasing in a concave down way, and it goes up 1 unit from 2 to 3. From 3 to 4, right, I'm going down -1, and again in a concave down way. And so there is that graph. Okay, so the inflection points on f is where f prime has a local max or min, right, where it goes from increasing to decreasing, because that means its derivative, f double prime, changes sign. If I look at f of 0 is 1, I am now starting here, but I'm going to do the same motion. I have the same thing. From 0 to 1, I go down 1 in a concave up way. From 1 to 2, I go up 1, right there, in a concave up way. And from 2 to 3, I go down 1, right? And we have a similar graph. Same thing if f of 0 is 2, right? This one right here. I have the same motion because I have the same derivative. My slopes are the same, so my graphs will look the same. The only thing that's different is the y values that they go through, but the slope of the green graph has to be the same as the slope of the blue graph has to be the same as the slope of the red graph for the entire graph. And so we get what we call a family of antiderivatives. All right. So here's another example. We have a graph of f prime. F of 0 is now 100, and we're going to use the fundamental theorem to sketch the graph of f, showing all critical points and inflection points. So again, if this is f prime, right here is where f prime slope changes sign, f double prime changes sign, and when f double prime changes sign, f has an inflection point. Okay? Also down here. That's another place where f will have an inflection point for the same reasons as given above. So let's take a look at this. So we're starting with f of 0 is 100, so I'm definitely going to use a different scale. And I want to think about, what kind of scale I want to use. So if I look over on my f prime graph, one rectangle is going to be about 100. So I want to be able to add and subtract hundreds. So I'm going to start with each, on this graph on the right, this is going to represent 100, 200, 300, negative 100, and so forth. So I'm starting at f of 0 is 100. We're going to start right there. Now, from 0 to 10, f prime, or this area right there, is 20 times 100 cut in two. It's because it's a triangle, 1/2 base times height. So that is 100 units. And I go up 100 units. Since f prime is going up, f double prime is positive, and my f graph is concave up. So I go up 100 in a concave up way from 0 to 10. So, and we'll keep this sort of scale. So this is my 10, this is my 20, this is my 30. Okay. From 10 to 20, I go up another 100. Remember, this is still positive area. F prime is still positive, so F is still increasing. But now, F prime is decreasing, F double prime is negative, and F is concave down. It's going to be concave down all the way to 25. So I'm concave down, so from 10 to 20, I go up 100 in a concave down way. From 20 to 25, now this is where I hit my local max also. Right here, F prime changes sign from positive to negative. So F has a local max, right? And that's what I'm finding. So I'm going to go down, and now I have the area, let's see, it's half of a half. So it's half of 50, so I think that's 25. So I'm going to go down 25 in 5 and in a concave down way, okay? And then here to here, I'm still negative. I'm still going down, but now again, F is going to be concave up on this part because F prime is going up and F double prime is positive. And so I'm going to continue to go down, but in a concave up way, another 25. So I'd end up there. And again here, right here at this spot, F has a local min because F prime goes from negative to positive. And then again, I'm going to go up, I think that's another 25 in that little half an area right there. Oops, so we should keep this the same. So some of my points, there we go, given their coordinates. So this inflection point right here, this is an inflection point at 10 to 100. This is a local max at 20, 300. Here's an inflection point at 25, and I think I came down 25, so 275. Here's a local min at 30. And again, I came down another 25, so that was at 250. And then finally, well, that endpoint, I think we can just leave that as it is. All right, so that's from a graph. You get the idea. Let's look at from a table. So I want to estimate f of x for x equals 2, x equals 4, x equals 6 using the values and the fact that f of 0 is 50. Okay, so my idea is that f of 2 is going to be f of 0 plus the integral from 0 to 2 of f prime of x dx. That's my fundamental theorem. So in other words, the area under the f prime graph. These are my y values on that interval. Let's take an average of those two y values as the overall y value. So f of 0 plus 16 times 2. That's going to be my average area of the rectangle. If I made one rectangle of the average of those two heights, and it would be too wide, and so I'm going to get 50 plus 32 is 82. Now I can do something similar from there. So f of 4 is going to be f of 2 plus the integral from 2 to 4. of f prime of x dx. And so if I'm going here to here, my average height for f prime is going to be 12.5. Right? I still have positive slope, so I'm still going up. So f of 2 plus 12.5 times 2, because that's the width of that interval, 2 seconds, and I'm going to get 107. And I want f of 6 in a similar fashion. F of 6, I take my f of 4, which I just had, and I'm going to add the integral from 4 to 6 of f prime of x dx. F of 4 was 107, so that's where I was. And then from here to here, the average height is 6. So let's say 6 times 2. So 107 plus 12, and I would end up at 119. And again, this is an estimate for all of those values. Okay, one last question. So given the graph of f prime and the fact that f of 2 is 3, so what I have now is this point right there. F of 2 is 3. Sketch the graph of f. Label the value of at least 4 points. So things that I want to know. Again, this is f prime over here. F prime. So right here where f prime changes, f has a local max. And right here, f has a local min. And right here, somewhere in here, right, f has an inflection point because f prime changes from increasing to decreasing. Similarly here, another inflection point is going to be there, and another inflection point is going to be there. So let's see what we have. So let's start at 2. So right here at 2, from 2 all the way to 6, I'm going to go down 7 because this is a negative area down there. So from 2 to 6 on the x, I'm going to go down 7. So at 6, I'm going to be 7 below, which is right here. Right there. And what I know is from 2 to about 5, f prime is going down, f is concave down. And that seems to be a good part of the area. And then from 5 to 6, I'm concave up. So something like that, a little more smoothly, but you get the idea. Now, from 6 to a little before 7, I am adding area. Let's see overall where we're going to end up. By the time we get to 8, I'll have added this area underneath, which would be 4. So by the time I get to 8, I will be 4 above where I am now, so I will be at the x-axis. And from x equals 6 to x equals about 7, f prime is increasing. F will be concave up. And then somewhere around 7, I start to become concave down. Now, the one piece we haven't accounted for is what happens before 2. Well, before 2, you can think about if I started at 0 and I went to 2, I would have to add an area of 2. So from 0, from x equals 0 to x equals 2, I must go up 2, which means from 2 to 0, I must go down 2. And so we look sort of like that. So this point is 0, 1. I have the point 2, 3 that they gave me. I know that this is the point 6, negative 4. And I know that this is the point 8, 0. There's my 4 points. So hopefully now you have enough to start your homework.